Okay, so in this lecture, we are gonna specifically cover two very important topics. One, we are gonna discuss some important properties. Let me just give an overview. First thing which we're gonna discuss is important properties of isomorphisms and and automorphisms and automorphisms. Okay, and the second thing which we are gonna introduce today is the concept of direct products. Under direct product, the first thing which we want to do is essentially introduce the concept of an external direct product, and we are gonna this I'm not sure whether I will be able to cover this today or not, but I'll have an intention to just at least introduce is as a definition the concept of an internal direct product. And if I am able to introduce the concept of an internal direct product in this lecture, then I'll also give a hint towards its correspondence with external direct product. Okay, I'll try to reach this point if possible, but I can't, guarantee it. But let's start with the first thing which we want to discuss today. What are the properties of isomorphisms and automorphisms? Okay. So what we're actually going to do is we are actually going to study two important theorems related to isomorphisms and then introduce the concept of automorphisms also as a very important theorem. Okay. So quick recall, what is an isomorphism? What is an isomorphism? So it's typically a bijective homomorphism, right? It's a bijective homomorphism. So it's a bijective homomorphism. And a very, very trivial observation, if I should say, for isomorphisms is that suppose you have two groups which are isomorphic to each other. Okay, these are two groups which are isomorphic to each other, and this is the obvious notation which we are going to use to denote isomorphism. Now, so this typically implies that there exists a map from G to G prime such that phi is bijective, right? Phi is bijective, and phi is a homomorphism, right? Now, since phi is bijective, so we can obviously define an inverse map of phi, which is from G dash to G. My question is, can we say that this phi inverse is also homomorphism? That's my question, and which has obviously an elegant answer that it's indeed a homomorphism. The reason being key, suppose you choose elements from say G prime. Okay, let x and y be elements from G prime. Then we know that there exists A and B in G because phi is obviously onto, such that phi of A is x and phi of B is y. Or the other way of saying is that A is phi inverse of x and B is phi inverse of y. What can I say about xy? Then xy is basically phi of A, phi of B, but phi of A, phi of B is nothing but phi of AB, right? Is this part clear? But then, so what have we actually, what do we actually have here? See, we could have also said this in this way that so what does this typically mean? This typically means that phi inverse of xy is equals to AB, right? But what is A? A is simply phi inverse of x, and what is B? It's phi inverse of phi. So this is indeed the definition of a homomorphism. Right? So what have we established in this fact is that if G is isomorphic to G dash, then G dash is also isomorphic to G, right? The second observation which I would say is that every group is obviously isomorphic to itself. Now, this obviously comes from the fact that isomorphisms are nothing but correspondence between the group structures, right? Other way of saying is that two groups are said to be isomorphic if their group structures are same. I'm not talking about the elements. I'm talking about the group structures. That is the composition of the elements, or in very simple words, the Cayley table, the operation table of a group of both the groups are identical, right? Irrespective of the elements they have. Now, obviously, a group will have the same Cayley table or the same operation table with respect to itself. Right? So, obviously, the sense speaks out the fact that every group must be isomorphic to itself. It's sort of very intuitive. But you can also observe that in terms of a map, that is the identity maps does the job, right? Right, if you simply consider the identity map from G to itself, then this is a well-defined bijective homomorphism, right? That you can justify on your own. The third property is also very, very observatory, that if you have a map from G to G dash such that phi is, a homomorphism as well as it's a bijective map, and you have a map, let's say, from G dash to G double dash, where phi, I guess this is psi, right? This is said to be psi, yeah. So psi is a map from G to G dash, which is an isomorphism. Phi is a map from G dash to G double dash, which is also an isomorphism. What can I say about phi composed with psi? So indeed, firstly, it's a map from G dash to, sorry, it's a map from G to G double dash, right? It's a map from G to G double dash. If I draw the diagram, so what do we have here? We have a map from G to G dash by psi and G dash to G double dash by phi. And then I can have a map from directly from G to G dash, which comes about as phi of psi, right? Now my question is this a homomorphism? No, it's obviously bijective, right? Composition of bijective maps obviously comes out to be bijective. There's nothing to prove out there because this is a bijection, this is a bijection. The bijection is naturally established here, but the question arises: is this a homomorphism? Answer is again very trivial because the map inside will get distributed upon composition of elements, and once it gets distributed, phi will also distribute. Right? That is, if I talk about phi of psi of xy, then there's nothing but phi of psi of x, psi of phi, because psi is a homomorphism. But then you have a distribution inside, so it will distribute outside as well. So it's phi of psi of x times phi of psi of phi. Right? So what does this mean? This means that so this means G is isomorphic to G dash. This means G dash is isomorphic to G double dash. And when we have both of these, then G isomorphic to G double dash. Right? This means G is isomorphic to G double dash. But what is the collective sense of these three observations, right? So I guess you people should have already understood what I'm trying to establish is that if I define a relation between groups such that a group G is related to G dash if and only if G is isomorphic to G dash. Okay. So we establish a relation between groups in terms of them being isomorphic. And the above three observations simply speak out the fact that this relation is indeed an equivalence relation. Is an equivalence relation. The other way of saying this is that the relation of isomorphism is equivalent in nature. Right? So that was a very, very obvious observation. Let's move on to the properties I want to discuss today. Okay, so let me just phrase it as a theorem. So if phi is a isomorphism from G to G dash, is an isomorphism, then we have the following observations. Number one, the identity elements gets mapped to the identity element. Number two is that for all integer n, phi of x to the power n is nothing but phi of x whole to the power n. Okay. Number 3, for all a, b in G, phi, what I want to say is that for all a, b in G, a, b equals b, a, that is a and b commute, if and only if phi of a times phi of b equals phi of b times phi of a, right? So a and b commute if and only if their respective images under the isomorphism commutes. Number 4, if G is a cyclic group generated by A, that is equivalent to saying that G dash is the cyclic group generated by phi of A. Number 5 is that order of A is same as order of its image in G dash under the isomorphism. Number 6 is that for a fixed K and a fixed X in G, and a fixed B in G, X to the power K equals to B has the same number of solutions, as X to the power K is equals to phi of B. Okay. And the final statement I would say that if G is finite, then the elements, the number of elements in G and G dash, of some specific order, uh, is same. Okay. That is if suppose G has 4 elements of order 3, then G dash will also have 4 elements of order 3. Okay. Now, if you carefully observe these statements, the only elementary proofs we require are number 1, number 2, number 3, and number 4. The rest of the statements will obviously follow from the first 4 statements. Okay. In fact, number 4 also, I guess it does not directly follow from 2, but it's somewhat related to 2. Okay. Yeah, let's check the proof of them. So proof, number 1, that okay, this proof is quite trivial, right? Because if you start with the image of 1 of the identity element of G, then it's nothing but the identity element of G composed with the identity element of G, but then you could distribute it out, but then you can simply use the left cancellation or right cancellation to say that it's indeed 1 of G dash. Right. Number 2, what can I say about phi of x square? X is any arbitrary element from G, so it's nothing but x times x, so it's nothing but phi of x times phi of x, but this is nothing but phi of x whole square. Now observe that you can just proceed by induction. If you assume that this distribution or this exchange of power happens for any integer n, then it will indeed happen for all positive integers, right? What can I say about phi of x to the power minus 1? Okay. Observe that. So, see, what I'm trying to say is that for n belongs to natural numbers, phi of x to the power n is same as phi of x whole to the power n, follows from induction, right? Follows from induction, and it's very easy to show it, right? So I'm not doing that honors now. Now, what about the negative integers? Now it obviously happens for 0 because that's the exact case we dealt with in number 1. What are the negative integers? So if I just show that this property holds for the exponent minus 1, then you can also proceed inductively for the negative integers as well, right? Because if n is less than 0, then it means n is of the form minus m for m being greater than 0, or m is a natural number. right? So if you show that phi of x inverse is phi of x whole inverse, then phi of x to the power n, which will come out to be phi of x to the power minus m, so it will be x to the phi of x to the power m inverse. But then you can, but m is a positive natural number, right? I mean, it's a natural number, right? So then it will be phi of x to the power minus m, and that's exactly equal to. So it suffices to show that this exchange of the power suffices. I mean, it holds for minus one, right? And it's also very easy to observe, because if you start with x dot x inverse, then this should be phi of 1 of g, and that should be 1 of g dash. Left hand side can be distributed, right? So it can be done as phi of x times phi of x inverse is equals to 1 of g dash. But then by left cancellation, you have phi of x inverse as phi of x whole inverse. You just bring this here by left cancellation. Clear? So this statement was also fairly trivial. Let's talk about number three. Now here's the important catch here. This statement has a one-sided implication for homomorphisms. Hence, the equivalence is not evident for a homomorphism, but indeed it's happening for an isomorphism. When we do the proof, you will understand why I am specifying this. See, if A and B commute, if AB is equals to BA, then that means phi of AB is equals to phi of BA. That's trivially because phi is a well-defined map. But then if you distribute on either sides, it means phi of B and phi of A commute, right? So there's no problem here. We just need to use the concept of homomorphism. But the converse is actually where we need to have an isomorphism, and it won't happen for a homomorphism. Reason being, suppose phi of A, phi of B is equals to phi of B, phi of A. So that implies phi of AB is equals to phi of BA. But that implies, by properties of homomorphism, if you just bring this here by taking its inverse, then you have phi of AB times phi of BA inverse is equals to 1. Right? Can I immediately write that AB times BA inverse equals to 1 here for an arbitrary homomorphism? Now, that's obviously something which we can't immediately write, because for us to write this statement from here, the map needs to be 1 1 or injective, because writing this statement after this statement, that typically means that the kernel of this map phi is the identity. That's exactly what means for it to be injective. Now, since we have an isomorphism here, this injectiveness is obvious. But for a homomorphism, that's not a general case. So keep that in mind. Um, Now from here it's obvious, right? AB is equals to B, right? Okay. Let's move on to the fourth statement. That is, if G is a cyclic group generated by A, so it's if and only if G dash is the cyclic group generated by phi of A. Okay. How can we prove this? Uh, See, it's quite obvious if we know that isomorphism preserves order, because G and G dash are already numerically equivalent, because phi is a bijection, right? Right. So if we deal with finite groups, then we know that if G is a cyclic group, then the order of G is same as the order of its generator. So if G and G dash have the same order, then their generators will also have the same order. And since A and phi A will have the same order, because an isomorphism preserves order, then this fact is trivial, right? We have not yet shown that isomorphism preserves order, which is our fifth statement actually. So we need to show this, you know, without using the concept of order preserving directly, which we can actually do, because see, since G is a cyclic group generated by A. Since G is a cyclic group generated by A, and phi from G to G dash is an isomorphism, therefore uh, phi A obviously belongs to G dash, right? So this means by closure, the cyclic group generated by phi A is contained in G dash, right? Okay. Now, if I choose an arbitrary element from G dash, let B belong to G dash. Now, phi is a bijective map, hence onto. This implies there exists some x in G such that x is mapped to B under phi. But that means there exists some element of the form a to the power k, because G is a cyclic group generated by A which gets mapped to B under phi, or phi of a to the power k is equals to B. But then from statement 2 we know that this is nothing but phi of a whole to the power k. So if B is some power of phi of a whole to the power k, then that implies B belongs to the cyclic group generated by phi of a, right? But B was an arbitrary element chosen from G dash. So that implies G dash must be contained in the cyclic group generated by phi of a. So we have a both sided inclusion, and hence G dash must be equal to the cyclic group generated by phi of a. Is this part clear? Okay. The next statement is the concept of order preserving, right? So again, here is the important catch, that order preserving is specifically for isomorphisms and not a general case for homomorphisms. We'll again see why. So let the order of A be A, M, and the order of phi of A be N. Okay. Now, what is a phi of A to the power M? So it's basically phi of A whole to the power M. But phi of a to the power m is basically phi of identity, which is 1, right? Because a to the power m is 1, because the order of a is m. Now we know that if order of some element is d and x to the power some k is equals to 1, then that implies the order divides that exponent. So from here it typically means that m divides the order of phi of a, which is n, right? Conversely, if conversely observe that what is phi of a to the power n, then that is nothing but so it's indeed 1, because order of phi of a is n, but that is nothing but phi of a to the power n, right? Now observe that phi is a 1-1 map. So if phi is a 1-1 map, so its kernel is the trivial subgroup. If it's the trivial subgroup, then that typically means a to the power n must be 1 as well, because a to the power n is an element from G which is getting mapped to 1, so it must be an element of the kernel of phi. But kernel of phi is the trivial group, that is the group consisting of only the identity element, and so n must be exactly equal to that identity element. But if a to the power n is equals to 1, then that implies n divides m, because the order of a is m. So this statement and this statement trivially means that n is equals to. Now obviously we again use the injectiveness of phi here, right? If phi is not injective, then we wouldn't be able to show this out, right? Okay. Now 6 and 7, they directly follow from first 5 observations, right? See, x to the power k is equals to b. This implies phi of x to the power k is equals to phi of b. But phi of x to the power k is phi of x whole to the power k is equals to phi of b. So identifying phi of x as an element y will give as y of y to the power k is equals to phi of b. Moreover, y and x are having the same order. So number 6 typically follows from the facts which we have already proved, right? And 7 also follows immediately. What was 7? I guess it was that G and G dash are having the same number of elements of each order, right? Because phi is order preserving, follows from the fact that phi is order preserving. So if I start with any element from G which has a specific order k, then it will eventually get mapped to an element which also has order k. So if I have n number of elements of order k, each of those elements will get mapped to an element of order k. So G dash will have precisely n number of elements of order k itself. Right? If it has n plus 1 number of elements of order k in G dash, then that extra element will also have an order k in G under the preimage of this isomorphism. So it's quite relevant, right? Follows from the fact that phi is order preserving. And this statement is actually quite important when we study group analysis. Okay, often we are concerned about the fact whether two groups are isomorphic or not, and in that case the first thing which we want to examine if the trivial observations don't work, right? We will see what trivial observations are, but if the trivial observations don't work, then the thing which we want to examine is that the number of elements having a specific order is preserved or not. Okay. And the trivial observations will come out now, where we study the properties of isomorphisms under groups. I mean, what properties do they carry for the overall groups? So let me again state it as a theorem. If phi is from G to G dash is an isomorphism, then number one, the order of G is same as the order of G dash. Okay, let me not write it because it's too trivial to be stated as a theorem. But that trivially comes from the fact that G and G dash are numerically equivalent because there exists a bijection between them. Phi inverse from G to G dash is an isomorphism. This we have already shown, right? This we have already shown while speaking of the fact that the relation of isomorphism is an equivalence relation. Number two is that if G is abelian, I mean G is abelian if and only if G dash is abelian. Number three, that G is cyclic if and only if G dash is cyclic. Now, I guess you people have already got the proofs of these statements directly from the previous theorem. If K is a subgroup of G, then phi of K, that is the image of all the elements of K under phi, is a subgroup of G dash. This is also very trivial observation. Now, if K dash is a subgroup of G dash, then phi of K dash, phi inverse of K dash is a subgroup of G. And number 6 is that the image of the center of G is same as the center of G dash. But all the proofs are obviously, they just carry out from the previous theorems. Because we already know that two elements in G commute if and only if their respective images commute in G dash. So that proves number 2. One we have already proven. We've already seen that if G is generated by, I mean G is a cyclic group generated by A if and only if G dash is a cyclic group generated by phi of A. So this follows directly from there. These two are very trivial observations. These two are very trivial observations. This fairly is same as the fact of saying that image of phi is a subgroup of G dash, right? This also comes very trivial. You just need to check, the subgroup criteria. 6 also follows immediately from the fact which gives the proof of 2. That if I choose an element A from the center of G, then it commutes with the whole of G. But if it commutes with the whole of G, then phi of A will commute with the whole of G. Whole of G dash, right? But then phi of A must be an element of the center of G dash. And conversely, if I choose out an element from the center of G dash which commutes with the whole of G dash, then the preimage of that element, which suppose I choose an element phi of A, which commutes with the whole of G dash. Then the preimage of phi of A, that's simply A, it will commute with whole of G, right? But then that element must belong to the center of G. So it's quite an obvious observation, right? So what do I mean by the trivial observations to check whether two groups are isomorphic or not? See, for them to be isomorphic, the first thing which we need to check is that whether they're bijective or not, at least, right? Because a homomorphism is a latter check. First, we need to check whether it's an whether we have a bijection or not. Right? That's I guess that's more important to check. So for for checking two groups to be non-isomorphic, we need to check just that some of these statements get false or not. So we need to check that the order of G is not equal to the order of G dash, because that says that there is no bijection between them. Suppose G or G dash is cyclic, but the other isn't, right? If one of the groups is cyclic but the other isn't. Similarly, if G or G dash is abelian, but the other isn't. Number four is that the largest possible order is not preserved. Largest possible order is not preserved. Now every order must be preserved, but seeing a group, the first thing which we get a catch about is its largest possible order, right? It directly comes out from the order of the group itself often. So just checking whether its largest possible order is not preserved will give you the fact that they cannot be isomorphic to each other. And number five is what I was trying to say, is that number of elements of a specific order is not preserved. Number of elements of a specific order is not preserved. Okay. Some immediate examples to establish this fact, I would say uh, that Z12 is not isomorphic to D. So we need to a 12 order group, so D6, which is not isomorphic to A4. Why is what is the reason? What is the largest possible order of an element in Z12? Precisely, it's 12. What is the largest possible order of an element in D6? It's precisely 6, right? Because we know that the element which denotes the rotation in D6 r to the power 6 must be equals to 1, and this is the largest possible order of any element in D6. What is the largest possible order in A4? So recall that A4 constitutes of all even permutations of S4. An odd cycle gives you an even permutation. So an odd, so what is the largest possible odd cycle in A4? It's a 3 cycle, right? So if it's a 3 cycle, then the largest possible order of A4 is precisely 3, because the order of a cycle is exactly equal to its length. So they are not preserved at all, right? Therefore, they cannot be isomorphic to each other. Similarly, we can say that Q is not isomorphic to Q star, where Q star is the group of non-zero rational numbers under multiplication. What is the reason behind that? See, every element of Q, except every non-identity element of Q, has infinite order. But in Q star, observe that -1 is a non-identity element, but it has a finite order because its square is 1. Right? That's clear. So we have two elements of order, at least, I mean, we have one element, one non-identity element in Q star, which has a finite order, but there are none in Q. Right? Okay. So I guess these observations were quite, observable. Let us talk about the next thing which I want to discuss is a property of automorphisms. That's also quite an important observation. Uh, so automorphisms. So what is an automorphism? So it's an isomorphism on a group. Okay. Phi from G to G is an automorphism. Is an automorphism whenever it's an isomorphism. So it's an isomorphism from a group to itself, onto itself. Now we denote. Okay, first let me say there is one very important automorphism which is called the inner automorphism. So phi we denote it as phi subscript G from G to capital G, such that the image of any element in capital G under phi of G is Gx G inverse. So this automorphism is called the inner automorphism, inner automorphism on G induced by small g. This had been covered in my previous lecture on automorphisms. Okay, so you can just go and have a look at that. There we had a broad discussion about automorphisms in great details. Okay, so what we had previously discussed in that lecture itself, and one thing which is kind of very easily observable out from here is that if AUTG, that aut G, denotes the collection of all automorphisms on G, and these are standard notations. INNG denotes the collection of all inner automorphisms on G, then both are groups. Then and the inner automorphism are groups. And what should be the exact operation, which is quite intuitive to notice, that under composition of maps. Under composition of maps, you can verify this on your own. That's very that's a very trivial observation. So verify. Okay, clear. What we are trying to show is that um, uh, the collection of all automorphisms of the group Zn is isomorphic to Un. So this is what we actually need to show for all n in. Okay. What a quick recall. What is Un? So it's I guess it's also called Euler group. I don't exactly remember what we call it, but it's also called Euler group, and specifically it's called the group of units. It's called the group of units. So what does this actually do? See, we already know what Zn is, right? So Zn is the collection of elements 0, 1 till n minus 1, which forms a group under addition modulo n. Right. What we try to do is that we try to construct a multiplicative group which closely resembles this group. Okay. But we know there are certain restrictions in that case. Firstly, we need to have closure under multiplication modulo n. Obviously, we need to talk about multiplication modulo n. So we must have closure modulo n. I mean closure under multiplication modulo n, and zero cannot be there. Okay, zero cannot be there. Because the identity element, if it's a multiplicative group, it's indeed one, right? And whatever operation you choose, be it multiplicative, I mean whatever operation in the sense, if you ever choose a multiplicative operation, you cannot get an inverse element of zero, because whatever we study, there always a convention we follow, and that's indeed quite intuitive, that zero cannot be equal to one in any case, until and unless there are some specific restrictions, right? For example, if you consider, if you have studied rings, then the trivial ring which you have, that is the ring consisting only of the additive identity, then that ring, now a ring obviously has an additive operation as well as a multiplicative operation, and it only has the element 0. Now 0 indeed is an additive identity, so there's nothing to talk about. But under multiplication, 0 will also act as a multiplicative identity as well. So if I set the convention of 1 denoting the multiplicative identity and 0 denoting the additive identity, then the trivial ring, which consists of only the 0th element, in that case 0 acts both as a multiplicative as well as an additive identity. In other words, symbolically 0 equals 1 in that case. Okay. But numerically, arithmetically, or in any other case, that's not an obvious thing which we consider. Okay. Yeah, so we are talking about the restrictions which we need to have to make Zn into a multiplicative group. Firstly, 0 cannot be there, and we must have multiplicative closure under modulo n. Okay, so if I choose any two elements A and B from Zn, both are non-zero, then when can we say that AB, uh, uh, so what I want to say is that when can I say that AB, or at least let me not talk about in this way. I want to say that this following, that if A is an element of Zn, Zn except the element 0, then when can A have a multiplicative inverse under modulo n? So this is a straightforward number theoretic problem. That is, I want to find a number B which is again from Zn such that B is also non-zero, such that AB is congruent to 1 modulo n. Now when is this possible? Observe that this is possible if and only if A and N are co-prime, right? How can we prove this out? Suppose they are co-prime. Let me just prove it out. Suppose they are co-prime. Then we know that we can write them as a linear combination which equals 1, right? There exists element B and say C in integers such that AB plus NC is equals to 1. But then having modulo on both sides by n, so this NC gives addition, this gives modulo 0. So this trivially means that A is congruent to 1 modulo n, right? What can I say from here? If AB is congruent to 1 modulo n, then that typically means that n divides AB minus 1, or that means that AB plus NC can be written as 1, right? But if AB plus NC can be written as 1, now D divides the left hand side, right? Suppose GCD of A and N is D, right? So if GCD of A and N is D, then D divides the left hand side. That implies D divides AB plus NC, but this implies D divides 1, so D needs to be 1, right? Therefore, to ensure a multiplicative group, we need to have elements which are co-prime to N. This gives rise to what we call the groups of unity. Okay. So basically, Un consists of elements A in Z, or you can talk about A in N. Let me talk about just A in N, because we already know that 0 is not an element, and obviously the negative elements are not to be considered because they eventually, because we are talking about modulo, right? We're talking about remainders. So the negative elements will comprise of positive elements if we talk about remainders, right? For example, minus 1 is same as n minus 1 under modulo n, right? So negative numbers you need not be considering. So A is in N such that GCD of A and N is 1. Okay, and this precisely gives you the group UN. Obviously, what is the order of UN from here? So it is basically the number of elements co-prime to N. So it's indeed phi of N, where phi is the Euler-Taussian function, which counts the number of elements co-prime to N. Below, smaller than N and co-prime to N. Euler-Taussian function, right? Okay, so yeah, that's quite good. So how do we show that uh, when automorphisms of Zn, it is isomorphic to Un, right? So proof. The proof actually requires an observation to be precise of the fact. What is the observation? So first, let me start with the observation. I don't think I will be able to introduce even external derived products in this lecture because it's already a 44 minutes long lecture. I'll do it in the next lecture. Observation that if I let us talk about the group automorphisms on Z10. Okay, if I choose any element from the automorphisms on Z10, then we know that phi of k will get mapped to. So now this first statement is obvious for Z as well, simply Z as well, because k can be written as additions of 1 k times. So then I can distribute this out. So it's phi of 1 and so on till phi of 1 again k times. So this gives you k times phi of 1. Now this k was typically arbitrary, right? If I talk about simply integers, then k was an arbitrary integer. So if I want to define a homomorphism, at least a homomorphism in Z, then the only thing which I need would be a precise value of alpha 1, or a precise value of 1 under the homomorphism. That's what we require. Similar in this case, alpha is an automorphism, indeed a homomorphism. So any element, the image of any element k from Z10 will get mapped to k times alpha of 1. So the only thing which we require to specify this map is a value of alpha 1, or a value of 1 under alpha. But now, what is the order of 1 in Z10? It's 10. Alpha is a automorphism, hence an isomorphism. So alpha must preserve order. So the order of alpha of 1 must also be 10. And indeed it's an, and alpha of 1 comes from Z10 only. Now what are the elements in Z10 which have order 10? So they must be the elements which are co-prime to 1. Sorry, which are co-prime to 10, right? This is a very trivial observation which we had studied while we were studying order of groups or cyclic groups, right? We recall that or if order of A is n, then order of A to the power k is n divided by n with k. So if n and k are co-prime, then order of A to the power k is also equals to n, right? What was this n? This n was the order of A. So in this case, we are talking about the generator of Z10. Actually, 1 is the generator of Z10. It has order 10. So every other element which has order 10 in Z10 must be co-prime to 10, right? Because in this case, n is 10 simply. In this case, what are the elements which are co-prime to 10? So therefore, phi of 1 can be 1 obviously, or it can be 3, or it can be 7, or it can be 9, right? These are the only 4 cases we have. So if we denote uh, alpha of 1 which is 1 to be, or let me just write it like this, alpha which sends 1 to 1 as alpha 1, which sends 1 to 3 as alpha 3, which sends 1 to 7 as alpha 7, and which sends 1 to 9 as alpha 9, then observe that the automorphisms of Z10 can comprise only the elements alpha 1, alpha 3, alpha 7, and alpha 9, where clearly alpha 1 is the identity map, right? Because if alpha k is equals to k times alpha 1 and alpha 1 is equals to 1, then alpha k is equals to k. So this is just the identity map. And the rest follows immediately, right? If I map alpha 1 to 3, then alpha k will be mapped to 3k, right? Let me just show the case for only alpha 3, let's say. That if alpha 3 is a well-defined map, that's quite obvious because, if alpha 1 is 3, then alpha, alpha of k is 3k, but we know that this is modulo 10, right? This is modulo 10. And we know that if x is congruent to y modulo 10, then 3x is congruent to 3y modulo 10. So indeed, this map is well defined, right? Right. Clear? And alpha 3, I mean, yeah, so we are talking about alpha 3, right? So alpha 3 here. And alpha 3 is onto by definition. It's you need 1, 1 as well as by definition, right? These two are very trivial cases. You can verify this on your own. Now, by similar cases, we can also show that alpha 7 and alpha 9 are also on bijective well-defined maps, which are indeed homomorphisms by definition, right? So the only elements which can which have which comprise of the automorphisms on Z10 is these are the only elements, right? So therefore, what more we can say is that see, if I talk about alpha 3 times alpha 3 under automorphism group, automorphisms of Z10, then alpha 3 times alpha 3 is nothing but alpha 9, because let me just be precise of this, and I will explain the general statement which you can verify then on your own, that what is alpha 3 composed with alpha 3, what is the element which you only need to check under here. So if I just check the image of 1 under alpha 3, that's precisely what we need, because every other the images of every other elements under alpha 3 will be then obvious, right? See, alpha 3 dot alpha 3 under 1, where dot is the composition operation, is nothing but alpha 3 times 3. But alpha 3 of 3 will be 9, right? So therefore, alpha 3 composed with alpha 3, it maps 1 to 9, which implies alpha 3 composed with alpha 3 is nothing but alpha 9. In the same way, you can check that alpha k composition alpha j is nothing but alpha kj, uh, kj modulo n for the case zn, or in this case modulo 10, right? Clear? Therefore, what is the Cayley table for automorphism of Z10? So, automorphism of Z10. Okay. So, we have alpha 1, alpha 3, alpha 7, alpha 9. We have alpha 1, alpha 3, alpha 7, alpha 9. So, alpha 1 times alpha 1 will be so we are just multiplying the indices modulo 10, right? So, this will be alpha 1, this will be alpha 3, this will be alpha 7, this will be alpha 9. Here you have alpha 3 because 3 times 1 is 1, 3 times 1 is 3 modulo 10. 3 times 3 is 9 modulo 10. 3 times 7 is 21, which is 1 modulo 10. And 3 times 9 is 27, which is 7 modulo 10. Similarly, 7 times 1 is 7 modulo 10. 7 times 3 is 1 modulo 10, which is 21. So it's 1 modulo 10. 7 times 7 is 49. So it's 9 modulo 10. And 7 times 9 is 63, which is 3 modulo 10. Similarly, 9 times 1 is 9 modulo 10. 9 times 3 is 27, so it's 7 modulo 10. 9 times 7 is 63, which is 3 modulo 10. And 9 times 9 is 81, which is 1 modulo 10. Observe that this group structure is same. That is, I can say that is that's I need to say it's isomorphic. You can observe that this is actually isomorphic to UN. I'm not giving the group structure. I guess you people have already understood what the group structure should be. I3 1379 1379. So 1 times 1 is 1, 3, 7, and this is obvious. We are just gonna go by multiplication modulo 10, right? U10, I should say U10. So you have 3 here, you have 9 here, you have 63, that's sorry, you have 21, that's 1 modulo 10, you have 27, that's 7 modulo 10. You have 7 here, 21, 1 modulo 10, you have 49 here. So 9 modulo 10, you have 63 here. So 3 modulo 10, 9 times 1, 9, 9 is 27, so it's 7 modulo 10, 9 times 7, 63, so it's 3 modulo 10, 9 times 9, 81, it's 1. So you can observe that these two are having the same group structure. Hence, automorphisms of Z10 is isomorphic to U10. So this observation is what we actually need to generalize. Okay. And I guess you people have already understood what map should we take to establish this generalization. Okay. So proof of automorphisms of Zn being isomorphic to Un. The map we actually require is a map T from automorphisms of Zn to Un via the T sends an element alpha to alpha 1, right? Because what we started with in the example, we started with an automorphism alpha and we checked that we can define alpha only by defining alpha of 1. That's what precisely we actually want to do here. Got it? Got it. Now this is again 1 by definition, right? This statement is 1 by definition because say suppose I say alpha 1 is equals to, suppose I say t of alpha 1 is equals to t of alpha 2. That would imply alpha 1 of 1 is equals to alpha 2 of 2, but then that would imply alpha 1 of k is equals to alpha 2 of k for all k in Zn, right? Because alpha 1 of k is nothing but k times alpha 1, alpha 2 of k is nothing but k times alpha 2. So alpha 1 of 1 and alpha 2 of 2 is alpha 2 of 1, alpha 2 of 1, so they just cancel out, right? So this part is clear. So it's obviously 1 1. And to define onto, just we need to specify an automorphism, nothing else. Let R be in Un. So how did we actually define them to be onto? So recall, then if I have a map alpha from Zn to Zn such that alpha of any element S is mapped to S times R modulo n, then we are done. That is exactly what we did the previous. So alpha 3 times alpha 7, it was giving to be alpha 21, but 21 is 1 modulo 10. That's what we exactly doing here. But then observe that alpha of 1 is R, right? So this implies T of alpha, which is defined as alpha of 1, is R. So for every element R in UN, there exists some alpha, because you can justify this to be an automorphism. That's a very easy check. It's a very easy check. It's 1, 1 and on 2 by definition, as much as I can see, by definition modulo n. And it's obviously homomorphism, right? Phi of S1 plus S2 by distribution, it gives you S1R plus S2R. So it's phi of S1 plus phi of S2. Right? You need to have an additive notation because we are talking about automorphisms on Zn, right? So for every element R in UN, there exists an automorphism alpha such that alpha is getting mapped to R. So it's indeed onto, right? What can I say about T being a homomorphism? What is T of alpha beta? T of alpha beta is alpha beta of 1, but that is exactly by composition. So we are talking about automorphism. So we know that they multiply by composition. So it's alpha times beta of 1. But then we can write it as alpha of 1 plus still 1. But this happens beta 1 times, right? But then we can distribute it out. So it's alpha 1 addition of alpha 1's beta 1 times again, right? Beta of 1 times again. But then that's nothing but alpha 1 times beta 1, right? So this is nothing but T of alpha and this is nothing but T of beta. Therefore, T is a homomorphism as well. So we have a bijective homomorphism, which means automorphisms on Zn is isomorphic to Un. What is the precise observation we get? That the number of automorphisms on Zn is nothing but the order of Un, but the order of Un is nothing but phi of n. So if you ever get a question that what are the number of automorphisms from Zn to Zn, where n can be any natural number, then that's precisely the number of elements less than n which are co-prime to n, right? That's a very fine observation. Clear? Okay. So let this lecture be up till this much. It's already 1 hour long. The next lecture we will be discussing about external and internal direct products. After discussing external and internal direct products, we are going to get into the concepts of the fundamental theorem on finite abelian groups, or the study of finite abelian groups precisely. So meet you guys in the next lecture.